Alright, so today we're working on sections 10.2, so we're basically going to be looking at the products and quotients of functions, and it's going to be kind of following the same lines of what we did yesterday. So basically you take two functions and we're going to either multiply them or we're going to divide them. Alright, and so to start off here, let's look at the product of functions. And so suppose we had two functions, f of x and g of x, and multiplying them produce the function h of x. We can write this operation in two different ways, both meaning the exact same thing. And I'm sure you guys can probably guess this, but if not, here we go. Or we'll zoom down, that works as well. Okay, so here we had h of x is equal to f of x times g of x. Or we can write this as h of x is equal to bracket f times g of x. Okay? And so here we have an example. We have f of x is equal to x plus 3, and we have g of x is equal to 2x minus 1. So we take f of x, multiply that with g of x, and that we produce h of x. So we take our f of x function, which was x plus 3, multiply that with g of x, which was 2x minus 1. We get this wonderful, once we FOIL out those brackets or expand them, we get 2x squared minus x plus 6x minus 3. Then adding all of our like terms, so just negative x plus 6x. And what we have is 2x squared plus 5x minus 3. Alright, so you multiply when, I guess when we're given that multiplication symbol. So multiply f of x and g of x, and that will give you a result of h of x when you collect all your like terms and simplify. Alright, so looking off to the right here, we have this wonderful graph. And so f of x here is this nice straight line here. This is x plus 3. And our function g of x is this nice other straight line here. And so what's kind of interesting to note is that when we're multiplying two linear equations, we get a quadratic equation. So we're left with a parabola, so that there is h of x. And I want to bring that to your attention again. Look at the coordinates. If you take, say, the coordinate of f of x, so it'll be, say, x and y1, and you take the second coordinate, or take another coordinate from g of x, using that exact same x value, but we'll end up with a different y value, so we'll label that y2. How to get h of x is you write down the exact same x coordinate, and you multiply y1 and y2. So what you'll be left with is y1 times y2, and that is your result for h of x. Okay? So you guys want to play around on your graphing calculators, but this is following the exact same principles as yesterday's section, so I'm not going to go into a whole lot of detail. You guys can try this out. I'll show this one more in depth with our quotient function, so okay? Moving down here, we are going to be talking about the quotient of functions. So suppose we had two functions, f of x and g of x, and suppose dividing them would produce the function h of x. We can write this in two different ways, once again, both meaning the exact same thing. So we could have h of x is equal to f of x divided by g of x. Or what we could have, I'm just going to write this over here, or just to make sure we have lots of room there, we have h of x is equal to, so bracket, f divided by g, and multiply that with the function x. So we're working with that variable x there. So there, that says the exact same thing. We're going to take f of x and divide it by g of x, and h of x there is what is our left or result. Okay? So here we're given an example. We have f of x is equal to 3x minus 1. And we're also given that g of x is equal to x squared minus x. So what our resulting product there is, we have h of x is equal to, so it's f of x, divide that by g of x. So we have 3x minus 1, divide that by g of x, which was x squared minus x. And just as a note there, it says that x cannot be 1 or 0. And so let's take a note of that. That is where we have asymptotes. And that's by looking at your denominator. So that was x squared minus x. That's where this denominator is equal to 0. So what you do is you factor out, pull out a common factor of x. We have x minus 1. So for this term here, x cannot be equal to 0. And for this term here, x cannot be equal to 1. That's when we get our non-permissible values. Okay? And looking over at the graph here, it looks kind of crazy. It's a bunch of things going on. But what here we can notice is here we have two asymptotes. This one here is at x is equal to 1. And this other one, it's not as obvious. You can't really see because of that y-axis there. But there's also an asymptote here. And this is at x is equal to 0, sorry. So we get this kind of crazy looking graph, and I can draw this over here for you ladies just so you can see it a little bit better. But if you want to also put, you can put this function into your graphing calculator and it'll help you see that a little bit more. But essentially what's going on is, so this y-axis here is an asymptote, and we also have one at, this will be x is equal to 1. And what's going on right in here is it kind of looks like it does a little bit of a tangent sort of graph. So kind of looks like it's doing maybe something like this, although it wouldn't be as curvy as I have it though. So that's for the inside in between our two asymptotes. And then what happens is that we kind of have maybe the graph of a reciprocal function. So where it's going along those asymptotes, the horizontal one and your vertical one. And then on the other side, it kind of does the exact same thing there. So you have, it's approaching those horizontal and vertical asymptotes, but it never actually does touch it. So this is kind of what our resulting graph there is. So that's kind of interesting to note when we have, when we're dividing. So this kind of has that interesting graph, and depending on what kind of functions we have, and depending how big they are or what kind of values we're given, they can create some pretty crazy graphs, kind of like what's going on over here. All right. So now, if I can, let's examine two coordinates and let's see if it follows that principle that we've been talking about throughout the past these past two lessons about the coordinates. Will f divided by g of x, will it actually be those y coordinates dividing into each other? So let's take a coordinate from f of x, and it doesn't matter really where you go along, but maybe what we can do is let's pull. It looks like f of x, where x is equal to -1, would kind of give us some pretty nice values. They're nicely at some whole numbers. That works out really nicely there. So let's go with x is equal to -1. So for f of x, that's this nice straight line here. When x is at -1, we are at y is -4. And for g of x, when x is equal to -1, that's this parabola here. When x is -1, y is equal to +2 there. Okay? So then what we're going to do is we're going to take -4 divided by 2. So what we'll have is -1. So remember that x value stays the same. So -4 divided that by 2 is -2. Now let's double check that. Let's find -1 and -2. And if you notice, that is exactly where our coordinate is for f divided by g of x. Alright? So hopefully that message there is starting to sink in, that you know, we can just take two coordinates as long as they have the same x value and then apply that operation to them, whether it's adding, subtracting, multiplying, or dividing. Alright? So let's move on to the domain and the range. Alright, and so kind of just like with everything else, the domain of a product or a quotient of functions is the domain common to the original functions. So that's exactly what we looked at last section, so hopefully nothing new here. So the domain of a quotient must also have the restrictions that the divisor cannot equal to 0. So that's one important distinction. When we have the quotient, because we have a fraction, you have to look at when we're going to have some non-permissible values. So that's, we're looking at g of x for that function. So looking at this, if I could just state that again here, that is for h of x, when we have f divided by g, we want to know when that g of x function is not equal to 0. That's your non-permissible values. And just like all the, just like last lesson as well, the range of a combined function can be determined using its graph. It's a lot easier to just graph it. It'll save you some work there and some guesswork. So you're better off just to graph it. It's a lot easier to see that way. All right. So now let's jump into a couple examples. We'll hopefully be able to finish one or two before the end of the video, if I don't color everywhere. Alright, so for this first example, here we let f of x equal to x minus 3, and g of x is equal to x squared minus 8x plus 15. And here we need to determine h of x, and this one here we're going to be multiplying the two functions together. So what we're going to do is we're going to have h of x is equal to f of x times g of x. Now we're going to replace f of x with its actual function. So be x minus 3 times this g of x function, so we're going to replace that. So it'll be x squared minus 8x plus 15. Then from there we can expand, or we can distribute this first bracket into the second. So we'll multiply each term by x. So h of x is equal to x times x squared is x cubed. X times negative 8x is negative 8x squared. X times 15 is plus 15x. Then we're going to distribute this negative 3 to each of the terms in our second bracket. So we have negative 3 times x squared. So be negative 3x squared. Negative 3 times negative 8x is positive 24x. Negative 3 times positive 15 is negative 45. Then combining like terms, we have h of x is equal to, so we have x cubed, then we have negative 8x squared and negative 3x squared, that there is negative 11x squared. We have 15x plus 24x, that is plus 39x. And then we have negative 45 there by himself, poor lonely little guy. And so this is our resulting function for h of x. So hopefully this question here is not too bad. So just remember, we have f of x times g of x, and you just multiply the two functions together and use your foiling, distribution, use all of that wonderful stuff that we've been learning throughout our whole high school career, if you like to say. So now we're getting close to our 50-minute mark there, so we are going to move over to video number 2. So if I could offer one suggestion, try number 2 on your own. This one is dealing with division. Although we haven't done an example using division, hopefully you guys kind of get the sense of what we're doing. So give that one a try, and then watch video number 2, okay?